Dear students, very good morning to all of you. Today I am going to start Module 5, Loop Antennas. What are the topics we'll discuss in this session? Let us see first the introduction about the small loop, comparison of the far fields of a small dipole and short dipole or regular dipole. So what is small loop? What are its characteristics? So look here. So small loop is a type of antenna where the antenna feed point would be in series with the loop. You know, antenna feed point is the bridge between the transmission line and the antenna. So that antenna feed point would be in series with the loop. And this small loop antenna which looks somewhat like a short circuit across the antenna feed, and this small loop antenna has a low radiation resistance and high inductive reactance. Because of this feature, because of the small loop antenna has low radiation resistance and high inductive reactance, impedance is difficult to match with the radio impedance, and this small loop is electrically small. So because of this, the current within the loop can be approximated to be constant along the loop, that is current flowing I is equal to I naught. So next we have, what is the radiation pattern of the small loop antenna? Dear students, the radiation pattern of the small loop antenna has the same power pattern as that of the short dipole. And the fields of the small loop have both electric and magnetic fields which are switched relative to the short dipole array. And the electric field in the small loop antenna is horizontally polarized in the XY plane, and this small loop antenna, which is often referred as the dual of the dipole antenna. Try to understand why it is called dual of the dipole antenna. Dear students, in the dipole antenna, the electrical current is flowing, but in the small loop antenna, the mechanical current is flowing. Hence, the small loop antenna often referred to as the dual of the dipole antenna or regular dipole. Here you are looking the different shapes of the small loop. So here the loop means it's the enclosed area. So you are observing circular shape, square shape, and it also turns out that the small loop antenna need not to be perfectly the circle or square in shape. So here the enclosed area is not important. The way the area is enclosing is not important. The perimeter length is very, very important here. So it may need not be a perfect square or perfect circle. Okay, maybe the irregular shape also possible. Understood? Why irregular shape is possible in small loop means, here the shape of the enclosed area is not important. The perimeter length is very, very important. Okay, these are the shapes of the small loop antenna. So next, how the loop which is related to the coordinates. Dear students, you are already aware of the different coordinate system like Cartesian coordinate system, x, y, z are the coordinates, then cylindrical coordinate system r, pi, z, and spherical coordinate system r, theta, pi. So here a small square loop which is related to the Cartesian coordinate system as well as the spherical coordinate system, also related to the cylindrical coordinate system shown in the figure. So next, what is the field pattern of the small loop? So the field pattern of the small loop is given by E pi is equal to minus E pi naught exponential of j psi by 2 plus E pi naught into exponential of minus j psi by 2. What is E pi naught? E pi naught is the electric field from the individual dipole, and xi is the phase difference. So this phase difference is nothing but 2 pi d by lambda into sin theta, and where 2 pi d by lambda is equal to dr, then xi becomes a dr into sin theta. Okay, xi is the phase difference which is given by 2 pi d by lambda into sin theta, but 2 pi d by lambda is equal to dr, then the phase difference xi becomes dr into sin theta. Dear students, from the equation 1, take minus e pi naught common. What you will get? You will get minus e pi naught into exponential of j psi by 2 minus exponential of minus j psi by 2. Next, what you can do? Multiply and divide it by 2. Then you will get e pi is equal to minus 2 e pi naught into exponential of j psi by 2 minus exponential of minus j psi by 2 divided by 2. See, you know the term exponential of j psi by 2 minus exponential of minus j psi by 2 by 2, which is equivalent to j sin psi by 2. Then e pi becomes minus 2j into e pi naught into sin psi by 2, which is nothing but minus 2j into e pi naught into sin of dr by 2 into sin theta. Substitute psi is equal to dr into sin theta. Next, how to construct the far field of the dipoles. See, you observed in the figure where the small the loop which is related to the different coordinate system. There you observed the 4 dipoles. Out of 4 dipoles, so here I am taking the 2 dipoles, dipole 2 and dipole 4. So these 2 dipoles which are separated by the distance d, which is nothing but lambda by 2 shown in the figure. And at the distant point we are going to find the electric field. So let us see what is the far field. What is the electric field at the distant point? Far field or electric field at the distant point, e pi naught is equal to j into 60 pi into I into L by r lambda, where r is the distance from the dipole to the distant point and I is the retarded current. Then e pi naught becomes j into 60 pi L into dr sin theta by r into lambda, but L is equal to d and dr is equal to 2 pi d by lambda. You will get e pi is equal to 120 pi square into I into sin theta by r into a by lambda square. Similarly, magnetic field h pi becomes e pi divided by 120 pi. So this you you are aware of the intrinsic impedance. Dear students, what is intrinsic impedance? Intrinsic impedance is the ratio of the electric field to the magnetic field. Here both the electric and magnetic fields are in the direction of pi. Then using that intrinsic impedance, we can write h pi in terms of e pi as h pi is equal to e pi divided by 120 pi. 120 pi is nothing but intrinsic impedance. Therefore, h pi becomes pi into I of sin theta by r into a by lambda square. So these are the electric and magnetic fields. So at the far fields. So next we will see the comparison of the far fields of a small loop and a short dipole. Dear students, what is the electric field in the short dipole? What is the electric field in the this small loop? Similarly, what is the equation of the magnetic field in the small loop as well as in the short dipole? We will see. See, in the dipole, electric dipole or short dipole, or you can call it as regular dipole, all are same. So in this type of antenna, electric field is given by e pi is equal to j into 60 pi into I into L sin theta by r lambda. But magnetic field in this dipole is j into I sin theta divided by 2r into L by lambda. But in the small loop, electric field and magnetic field equations are given by e pi is equal to 120 pi square into I sin theta by r into a by lambda square, and magnetic field is pi into I into sin theta into a divided by r into lambda square. So these equations which distinguishes the small loop and the short dipole. Thank you.